So yeah, today we're gonna finish going through a lot of the features and additional tools you'll need to use to get your deep learning networks running. These are like the main key tools that go beyond setting up your system architecturally and then choosing an optimization scheme. Okay, but before we get into that, I wanted to just take some time to talk about the class project. The details of it are at the course website / just click on the project info tab. You can be working on it alone or in a group of up to 4 people. The point of bringing this up now is to encourage everyone to start thinking about the project. The way it's going to work is you'll get some data. You need data to train a deep learning network, as we've learned. Because we're focused on supervised machine learning, the data should consist of images, and we're, of course, focused on imaging. So some sort of image data, preferably, and then labels, right? Labels being what you're trying to teach the network to turn the images into or decide about. The data set can be from a lot of places. So in that link, there's a number of linked to data sets that are available online. There's even more if you just Google for data. There's actually databases of data that you can use. So there's plenty of data out there, which wasn't the case when I started teaching this course, really. So it's really easy to find image data, specifically like biomedical image data is all over the place, but in general. But you have to be cognizant of the image data you're selecting, because really a focus of the project is to analyze the physical imaging system that you or the data was acquired with, or that you're interested in simulating or better developing an understanding of, right? So that is really the focus of the final project, or half of the focus. The final project is not simply downloading an image data set and then maybe changing it a little bit and then passing it through a downloaded neural network. I have a 7th grader I know has done that in like an hour. So that's not a final project. It's not just showing that you could take image data and pass it through some Python code that you download. So really it's about developing an understanding of how the images were acquired, and as I'll talk about on the next slide, trying to optimize, ideally, aspects of that image acquisition process. Okay? So you'll submit the code you've written to do that. Final project, short paper. Yeah, something, I don't know, those page numbers might not be correct. I feel like we changed them. But like 5 pages is good. And there's specific sections you should include, right? So it's like a little research paper. If you've written one of those, then you know kind of what I'm talking about. If not, it's outlined on that website a bit more in detail. And then, yeah, there's a little web template. You just like put your abstract in a picture that we can then use to post on the web. And really the web is like an internal source. It's not necessarily externally facing. You have the ability we give you a little questionnaire that says if you want to allow others to see your little template, which essentially lets other people who take the class next year see what you did for your final project to get a better idea themselves, which you have the ability to do also at the deepimaging.github.io website. You can see a bunch of other projects. And then really, yeah, the end is you'll present on this. So you'll create some slides and present to the class about what you did. Okay. Yeah, it's a group-based presentation. So yeah, this course is kind of the same size as it was the last year, and we can squeeze them into the finals period. Usually it turns out to be whatever number of presentations is times whatever 8 to 10 minutes equals 3 hours, which is the final slot. This is just a little bit more detailed about what should be a component of the project, so you all can really start thinking about what you want to explore. In 3 or 4 lectures, we're really going to start talking more about these points. We're going to loop back and begin to take our machine learning models and connect them to imaging systems and how you can model them. So this will become more and more clear over the next month, but we won't get to it for another couple lectures. So I just want to talk about it now because, again, it's kind of a good time to start thinking about your final project earlier rather than later. So yeah, what we're going to be working on is not just examining images, taking them and classifying them, for example, but beginning to try to use the machine learning network to optimize how those images might be acquired for better classification or for a specific task that you're interested in performing. There's also parameters you can change or alter within the image that then allows you to examine how those parameters might impact the ability of systems to classify or segment or detect objects within them, right? And really it's about kind of system level analysis, right? We're all engineers. The goal is to begin to explore ways to improve or understand the imaging hardware that you can either assume exists and has captured the data, or that you're interested in designing and you're using the data to inform, or that you are currently working on as a research project and if you're a grad student. Exploring different axes of those performance criteria and performance limits, right? And so it's not just like, oh, can we get better performance in our machine learning algorithm, right? That's just one axis. There's all these other axes that matter when data is captured, right? So those include resolution, the speed of image capture, the size of the imaging system that you could be considering, right? Its weight, how much power it's using. And so it's really thinking in terms of that is the goal, right? So it's like, can I design a better imaging system that's much smaller to capture pictures of X to then be classified, right? Or can I create, even if it's really noisy in this context, an X-ray, chest X-ray system, if I really lower the dose to improve patient safety, the images will get much noisier, but can I then still achieve this machine learning goal? Or, you know, if I really want to look at thicker specimens under this electron microscope, then the image data will likely, you know, alter this way, and can I still achieve classification? Or could I even classify how thick the sample is in addition to what's in it in my electron microscope data, right, to help with not having to slice them so thin, right? Is that kind of all clear? I'm just making examples up on the fly, but there's really like so many things you could think about. Broad ideas are great, but it's simply connecting them to some sort of characteristics of how the pictures were taken or in what context they were taken, right? And again, this will be more clear. We'll have lots of examples. We'll go through code to do this sort of optimization. But that's what you should be thinking about. Okay, so what are the next steps? Discuss with others in the class. Feel free to use Canvas to discuss with others, right? If you're like, hey, I'm looking for a project partner, or, right, hey, I want to work alone, but I'm struggling to find some interesting data set related to X or Y. Post it and we'll help, or others can help, right? It's collaborative in that sense. There's a lot of other projects posted up. You can look at those for inspiration. A lot of these ones from previous years, we were really focused on optimizing specific parameters of the image acquisition process to improve performance for certain machine learning tasks. But yeah, the final project scope has since like kind of become a bit broader than that, so it doesn't necessarily have to be as targeted towards joint optimization as in previous lectures, but that's a great topic and goal. So if you do choose to do some joint optimization, which means you're going to optimize within your neural network some parameters of image acquisition in addition to the image analysis, reclassification, or segmentation, which again we'll talk about a lot in a few lectures. That's a great topic. It really satisfies what this final project's all about. The goal is to write like a paragraph or two about your idea, and then you're going to submit that to make sure, A, that everyone is on the same page if you're working in a group, but B, that the project is a good one, right? It'll be achievable, good in the sense that it'll be achievable, because we've had scenarios where people try to bite off more than they can chew in this relatively short period, especially when you don't have annotated data. You're trying to annotate the data yourself to then create a data set to then start the final project. That can become problematic. And then B, to make sure the topic you're considering is a good thing with enough analysis to it. I'll send out final dates about that, or I'll show them. And then, yeah, the final project will be presented during our final exam period. So here's our model, just as a refresher. I'm not going to dwell on it, but we have our ability, let's say after training, to evaluate images X and create vectors Y really easily with this 3-layer neural network. We've seen this all in code right now, right? So the box on the right, that's this chunk of code that's pretty easy. If you can import the data directly, that's great. If you can get it from Google Drive, that's great. If you have trouble otherwise, then that black box can be pretty tricky, right? You might spend a lot of time on that in your final project. If you have the data yourself from your lab or whatever, and it's not organized well and the labels aren't uniform or something like that, then that's going to be a tricky box. This blue box is really easy, right? We saw it in Keras. It can be really easy. It was like 5 lines. That was our model architecture, right? It was just adding a few lines. You can add more and more conv layers or different nonlinearities, right? So this function f is really flexible. The training process, we'll talk more about today. You just set up a loss function, and that's also a few lines of code, right? The red box on the right. So it's all straightforward. What really we haven't learned about is how do we do weight update? Like, how does this actually work when we hit enter and this loss function is minimized? How does TensorFlow do that? It's going to do it, but we're going to learn about how that works. We're going to talk about auto differentiation for a lecture because it's interesting. And you should know how it works, because then if it doesn't, you'll understand why. Okay, and so we're on this right side of this CNN component list, and we've talked a lot about this already, and I'll just quickly refresh everyone's memory. Last class, I presented these different loss functions you can choose from. Again, these are easy to just type in and update. You can just Google TensorFlow loss functions, and you'll get a much longer list than this because people keep adding different loss functions. You can just define your own as well. You're not limited to the fixed functions within TensorFlow. Okay, so another idea that is useful to talk about because you have the flexibility to apply it, especially in situations where you're considering image segmentation, is regularization. So we already spoke about regularization. If this sounds really new to you, then you should read about it. It's kind of a well-known addition to cost functions. You take what you're doing and add on an additional term, r, where r is a penalty. If you're adding values to the function you're trying to minimize, it's going to make it larger and thus penalize it. It's called a penalty term. And r can take a lot of forms, right? So you can regularize here the weights in case you are using the weights of your neural network to inform ideas about your imaging system. Again, something we'll talk about, but right now we're just thinking of weights as these abstract variables that allow us to classify. What if the weights actually had some meaning, right? What if you were using weights to then assign variables to certain amounts of noise, or turn certain pixels on and off, or select certain images from a set, right? All of those are things that are easy to do now with TensorFlow, allow you to optimize components of imaging systems, and should have particular values, right? Or you might want to say, hey, the weights can't be negative, or the weights should be 1 and 0 and not any value, right? So that's something else you can achieve via regularization. Common regularizations that help specifically for preventing overfitting are an L2 regularization. So here it's the sum of the square values of the weights. L1 regularization is the sum of the absolute values. So why does adding up the sum of the squares of the weights help prevent overfitting? Here's a simple picture. So if we have a vector of weights that's kind of peaky, it has one value that's 1 and lots of other values that are 0, that could be one possible function that we're going to use to draw a classification or a boundary, right, let's say. And a second option is the weight vector that's 0.25, 0.25, 0.25, 0.25, right? So in each scenario, they'll classify this input example x to the same value, 1, right? Assuming this is a linear classifier. But if we apply a regularizer, right, the sum of the squares, this vector here, is going to be smaller than the sum of the squares of this vector, right? 0.25 squared plus 0.25 squared, blah, 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 equals 0.5, right? Pretty sure. Anyways, it's a smaller number than 1. So W1 squared is just 1, right? Plus 0, plus 0, plus 0. So if the loss function was minimize this difference without the regularizer, right, both of these evaluate to the same value, and so they'll yield the exact same loss, right, like a mean squared error loss. But if you add this plus regularizer, then the loss function will pick the lower of the two, and it'll prefer to pick W2, right? So you'll preferentially tell the neural network, hey, W2 is a better choice than W1, right? And so in the context of considering weights for larger vectors, it does require the neural network to select vectors where the weights are more uniform. They're more bounded towards a central mean than distributed. And so in the context of examining these classifications, that generally translates to lines that are less curvy and more generally broad, right? And so that means they'll fit more generally and not overfit your data during training. Does that make sense? So in summary, when you add a regularizer, that's the square of the weights, you will promote or encourage the network to train to models that don't overfit. They're not going to be these very wiggly lines drawing the boundary between two data sets. They'll be more general. Okay, so here we're going to just quickly outline a few particulars about how the gradient descent actually operates in TensorFlow. The bread and butter method of gradient descent in TensorFlow is to do something like steepest descent or conjugate gradient descent, which is a relative of steepest descent, which we've already discussed. But it's done in a way that's stochastic, right? So now I need to describe what this stochastic term means. In regular gradient descent, you'll evaluate the gradient across a set of data, right? And so we've seen this term before a lot. We have a loss function that's the average of the error, the loss, that accumulates over a set of n examples. So in MNIST, we have n equals 60,000 in principle. It's a lot. As data sets have gotten larger and larger, there's just been a general inclination to not consider the entire data set in evaluating the loss function. That has dovetailed with the idea of stochastic gradient descent being a good method. The insight that this term stochastic brings to the table is to not use all of the data each time you evaluate a loss and take a step. You look at a small batch of data. The batch is called a mini batch sometimes, or a batch size. It essentially is a number that's up to you. So common batch sizes you can select are 32, 64, 128, depends on the size of your image, the amount of memory you have available, and the amount of stochasticity you want to introduce to your optimization process, which I'll talk about in a second. But it's a term you need to define, right? Why are they these decades, 2 to the 5th, 2 to the 6th, 2 to the 7th? I don't think they have to be. I think computer architectures are advanced to the point where that property doesn't have to hold. Like, you won't see a jump in performance because it's 32 and not 33 anymore. What stochastic gradient descent does is it first creates a batch. You select a subset of the data, and then you evaluate the gradient descent with that data batch, and you update the weights. That's it. So this term stochastic is introduced because that selection process is semi-random, right? So stochastic processes have that property of being semi-random. Okay, so why does this work, right? Why does gradient descent still work when you aren't looking at all of the examples, but just little subsets of them? It's a natural question. So let's say we have a loss function L that we can consider over all examples at a particular iteration. We're going to have some weights, and then we can consider all training examples, all n of them, pass them through the network, and see which weights we should decrease and increase to make the loss smaller across all of those inputs. The gradient tells us which direction to move to do that, right? The gradient is saying these weights should be larger, these should be smaller, go in that direction in the space of weights. That is this red vector. For each example, each image will have its own gradient. A single image in your data set will pass through the network, and you can turn the weights this way and that way to better classify that particular image. So they'll have different vectors, each for a single image in this weight space as well. This red vector is the geometric mean, or the mean, right, literally, of those vectors. So that's that 1 over n. And that's kind of written here, just mathematically. The gradient operator just moves into the sum. So the loss is the mean of the loss. The gradient of the loss is the mean of the gradients of each loss. And so the argument of stochastic gradient descent is if you get rid of some of these blue vectors, you don't have n of them, where n is really large, 60,000 in even the simple example we considered, but now a much smaller number, and you look at their mean, which is the purple arrow, it's not going to necessarily equal the red arrow, right? The mean over a much fewer number of gradients, sub-selecting all those blue arrows, just choosing a few, will not equal the mean over all of them. On average, the purple arrow, which is the mean over the mini batch, will approximate the red arrow, the global mean, if you sub-select those arrows randomly and you do that repeatedly. Right, so in other words, stochastic gradient descent works because you're taking many iterations and you're selecting examples randomly. Under those two criteria, you can prove that this gradient that you're trying to go down the hill with each step is generally well approximated by a purple gradient, the sub-selected example gradient. Right? So it's kind of an average argument. How do these really work? We're going to talk about that. I'm going to kind of give a preview for next class, because we're going to start seeing these computational diagrams. The way TensorFlow actually solves gradient descent is it takes your problem and splits it into a connected graph like this. So you have x's and weights. They'll, in this linear classifier, get multiplied together. Right? TensorFlow will treat this as an operator that has a gradient assigned to it. Right? If you take the gradient of the multiply operator with respect to x, you will get w. Right? If you take it with respect to w, you'll get x. Right? If this was a squared operator or divide operator, it would not give you that. It would give you something else. Right? The people who wrote TensorFlow had to assign a subfunction for every single operator that you can type into TensorFlow. And then it'll go on to a next operation. So let's say you take the difference and square them, for example, or I don't actually know what hinge loss is. I guess it's this max operator. There is a function that takes the max between the difference of two inputs plus 1 and 0. We'll talk through this slide in detail, but that is an operator, and that has a derivative, right? The derivative of that, if the resulting value is less than 0, is going to be 0, right? Because it's that ReLU type shape, and then if it's greater than 0, I don't know what the derivative of that is. It's some weird expression. But someone had to code that into TensorFlow, right? And so when you hit enter and you want to update the weights over here, TensorFlow is going to kind of go back step by step through this graph. That's what this term backpropagation is. At each step, it's going to multiply the gradients just the same way we would do with the chain rule, to kind of pass our derivatives through different operations in an equation. Okay. And then it reaches all the way back here, and it still maintains the gradients, or it knows how to change the weights accordingly due to all the operations in front of it. The rest of this lecture, we're going to talk about these details down here. So these are all terms that I'll define, but they're important concepts to keep in mind to get your code to work. Because just at a minimum, I showed code on Monday that had a few of these features in it that I skipped over, and the code worked. But even as things get more complex, you need to also adopt some of these more advanced concepts. Right? Specifically, we showed Dropout last class. And that's it. I didn't do any normalization, or we didn't augment the data. And then we just did kind of vanilla gradient descent. So we'll talk a little bit about some of these features. Okay, so let's start at the beginning. How should you initialize your weights? That's a choice that's up to you, right? You're gonna start your optimization process with your data and just some random weights generally. So you don't have to choose random weights. You can start with uniform weights. They can all be 0. It's not a good choice. They could all be 1. Not a terrible choice, but you know. So the question is, what should you do? And this is one suggestion. You use something called Xavier initialization. We were actually, a student in my lab worked on a project where we thought another initialization procedure was going to be way better, required to achieve the task. And we kept running into issues, and it turned out when we switched to Xavier initialization, everything worked, right? So it really does matter sometimes how you initialize the weights, because without choosing this particular method, or just, it's a very simple method, I'll explain, we got from something not really working to something actually working. And so when you initialize your weights, you generally write in TensorFlow something like this. You say, hey, I have some weights, and I want to make sure they're variables. Remember the key term tf.variable, critical, those are the weights. Each time you write that, you're going to create a set of things that TensorFlow is going to optimize to try to drive the loss function to be as small as possible. The weights here we're initializing as a truncated normal distribution, right? And so when that tf.truncated normal creates a vector that's like a random normal distribution, right? So in MATLAB, it's like rand_n. It's like a rand_n call, but it doesn't allow the values to get too large, right? It doesn't say, hey, like there is a 5 sigma probability that a weight could be 17 when the standard deviation is like 2, right? We don't want that, because if the weight's too large, we already talked about how they can cause the neural network to not work well, because, right, the nonlinearities lose their applicability often at large weights and small weights. Okay, so that's the truncated part. And then the standard deviation's up to you, right? What do you choose for the standard deviation? Here it's 0.1. Seems like a good random choice, right? So Xavier initialization says don't choose 0.1, choose something else. What should you choose? So the insight is that the variance that you're passing through your first layers, you want it to stay the same. So you have some inputs x and some weights, they're going to multiply by them generally. The variance of the input should pass through the weights and remain the same, right? The variance across x after the first layer should then produce an output that, when you take var of the output, should match var of the input. Okay, that's what Xavier initialization tries to achieve. The simplest form of Xavier initialization is just considering an inner product with weights, so a linear classifier or a linear. So convolutions are pseudo-linear. It's W transpose X is a good approximation of what's happening. You can get a little fancier and actually account for the convolution operator. But let's assume the first layer is just this inner product, W transpose X, where W are your weights and X are the input image pixels. If you take the variance of both sides of this equation, you'll get an expression as follows. So the variance of the output of the first layer will equal the variance of all of that inner product, W1, X1 plus W2, et cetera, et cetera. If you assume that those are all independent, which is okay, maybe because all the weights you initialize randomly, then it's equal to n times this variance of a weight and a pixel, right, on average. So what's the variance of one weight times one pixel? Well, it's equal to the variance of A times B equals A squared times the variance of B plus B squared times the variance of A plus the two variances multiplied. It's some identity. And so then what you have already assigned in the previous code, what you should always do when you create weights is make sure there's zero mean. Right? And in the next few slides, I'll explain how TensorFlow, even as you optimize layer to layer, it tries to maintain the weights as zero mean. Why is that? Well, again, we don't want the nonlinearities to move outside of their region of influence, right? The sigmoid or tan H, remember, type nonlinearity. If the weights are way over here, the nonlinearity is not going to do anything. So you want to avoid the scenario, okay? And so by having the inputs be zero mean, you remove this first term. The weights, initialized weights, be zero mean. You remove that first term. Okay, so then we have these other two terms left. And so what you also want to do, and we already have done on homework 1, and you want to keep doing through all the homeworks and on the code, is take your data and subtract its mean from it before you input it into the neural network. So all of your x's should be zero mean too, right? I'll say that again. All of your images, every time you input them into a deep neural network, you should subtract the mean from them first. Okay? That again helps with this problem. Okay? So that removes the second term. So all we're left with is this third term. All right, so now you have the variance of y equals n times the product of the two variances, the variance of the weights and the variances of the input pixels. And so you can maintain the variances. The output variance is going to equal the input variance when the weight variance equals 1 over n. Right? It's pretty simple. And so in Xavier initialization, you make this value 1 over n for your first layer. So n is the number of pixels. So if you are inputting a 500 by 500 pixel image, your variance of your weights is going to be 1 over 500 squared. If it's some other number, it's going to be a little less. And of course, you can get kind of more fancy with it. All right, that's to start everything off. And you can just play around with that. It's an easy parameter to change, but it does make a difference. So data augmentation is something else you need to think about ahead of time. It's kind of a simple thing that is intuitive, but there's a lot to it. So you can kind of go crazy and do lots of stuff with data augmentation. You can, people have thought about it for their final project to optimize different augmentation regimes. So data augmentation is really straightforward. You have, let's say, 60,000 handwritten digits, or probably in many of your cases, let's say a few thousand images that you're going to download, right? Which for deep learning networks isn't that much. It sounds like a lot, but it's not. And so you want to have more data. And so for a computer, right, for us, you look at this image and you rotate it a little bit. To us, it's sort of the same thing, right? It's like, oh, that image, it's just the image rotated. But for a neural network, it doesn't know that. And the values right around, like here, are mostly low values, and they're green. And so that part of the neural network, the convolutional kernel, when it hits that, will then really have certain weights going on to the next layer, et cetera, et cetera. If you then just take this image and rotate it, now the values that were here are now bright orange ones. Right here is occupying those pixels because you rotated it. And so the neural network will see dramatically different numerical values coming in. And so it'll really change the weights and how they're going to be updated, even though the classification is the same. It's still a cat image, for example. It's still going to result in a vector that's 1, 0, where 1 is probability cat and 0 is dog, right? And so data augmentation is simply doing these image transformations to then give the network more data, more information, more examples to feed its hunger for data, because the more data your network gets, the better it's going to perform for training. Okay? And so rotation's one type of augmentation. You need to start thinking about this, though. Depending on your application scenario, you want to use particular augmentations. Let's just say that. Okay? So flipping the image upside down could be one form of augmentation. Depends, right? If you're designing a camera phone and your goal is to classify images of cats and dogs, I would say the flip upside down isn't a good idea, because rarely will you capture a picture of a cat that's upside down, right? Because the camera can like auto flip and make sure when you're holding it upside down, it'll rectify itself. But if you're designing a microscope, for example, and you can put a sample in any which way, the slide can go in like this or this, right? No one really knows or cares which way they're putting the slide in often. Then, yeah, flipping it like this would be great, right? Because that'll realistically reflect normal use cases. So a lot of these are baked into TensorFlow. There's two choices. You can either take your image data and pre-augment it, or you can use TensorFlow to augment it. TensorFlow has its own little pipeline. I prefer pre-augmenting. It just is easier, but uses more memory, right? You kind of have to save it all and then pass it through. So it's kind of up to you and your application. Color is a really important one. So I would say probably the most important augmentation to consider are these two: color and adding noise. Adding noise is always good. All right, we'll return to this. But adding random perturbations to your data or your neural network helps always. Training a neural network is kind of like training a young person how to ride a bike, right? And so to get them to really know how to ride a bike, you kind of want to push them a little bit. Have them sway to the side, left and right, right? Randomly give them little things to worry about to make sure they don't fall. So that's really what this noise adding is doing. It's pushing your network by giving it those, hey, here's a random thing, here's a random thing. You better still handle this, right? You better still classify this as a cat, even though there's all these random perturbations. It's a form of regularization. You should definitely use it. It's one of the first things I tell people to do when they're encountering trouble and it seems like their data set isn't large enough, right? You can quickly increase the size, the apparent size of your training data by a factor of 8 or 16, right? Or something like that. If you just first augment the color, and then from that augmented color data set, start to add 3 levels of noise. And then from that, start to shear each example a bit. So you have your first weights initialized. You have your big image data set, right? Because you augmented it. And now you're ready. And you start passing these images into your network. So what else do you want to make sure to do? Well, I've kind of already said this. Before you get the image data in, you want to normalize it. So I already said you want to have it mean subtracted. Well, it helps with that Xavier initialization problem, right? So that's one reason. Reason B is this problem, right? If the images have large values that aren't zero mean, you're going to immediately be in this regime, or rather this regime, because they're all generally positive valued pixels that you're going to input, and they're going to cause outputs that are large valued. And then you also want to divide the image by its standard deviation. And so that was in the code I showed on Monday. That was in the code that you guys downloaded for homework 1. And the reason, again, is to keep the convolution, generally, that you're going to first apply in your first layers between your weights and your pixel values x to not be too large. The output of that should be kind of between -2 and 2. So that's the first layer. What happens at subsequent layers, right? You can have like really quickly 20 layers of comms. You just keep adding them in your code. So how do the weights not get all crazy, and how do the values not change too much going through that? So that's where batch normalization comes into play, or these different normalization schemes. So you may have heard of batch normalization if you've read a bit about machine learning. It is kind of the default technique now, but there's other types of normalization. All of them attempt to solve this same problem of keeping the values that are output each layer before the nonlinearity is applied to be close to the mean 0 and not too large, not too small regime. Okay, so this batch normalization paper, I don't even know, I didn't check it recently, but it's been cited in an ungodly amount of times. It's like probably now in the 50 to 100,000 citation regime. So everyone uses it, right? What is batch normalization? It's a pretty simple technique. It applies the same type of insight. So the inputs, right, we've mean subtracted and normalized by the standard deviation. You want to maintain the weights to have a similar type of property, okay? So before batch normalization, you would have these inputs come in and they're nice 0 mean and centered towards 0. But then they start to get multiplied by some weights. And slowly you would get this shifting of the mean of the output of each layer to be really negative or really positive, right? And that would cause neural networks to fail, right? That reason alone prevented the discovery of deep neural networks for 30 years or more. And the reason why no one did it is because of this covariate shift problem. And you can read about it. These normalization techniques that actually work really took regular machine learning and made it deep learning, right? I think people say it's, oh, the computer memory and we can take 1 million images and do all this stuff. That's not true, because when I was in grad school, we had the tiny image data set that had 1 million images. That was like way before convolutional neural networks. So it's not that. It's these batch normalization techniques and things like that that really made a difference. Okay, so what is batch normalization? You might naively say, hey, I'm just going to take my output of my neural network at each layer and make sure it's 0 mean and divide it by its standard deviation, right? Right, just like I did to the first layer, or to my input data before it went into the first layer. There's nothing saying you can't change the weights a little bit, right? It might throw off your optimization process, but if you keep doing it, maybe you'll get lucky and they'll still converge. And so the reason why that doesn't work is in most nonlinear functions, if you just always keep the values to the same regimes, right? This regime is generally, it's either going to be linear or apply the exact same transformation. So it's not expressive, right? You're going to be repeating the same pseudo-linear transformations, right? And so just taking the output of each layer and saying, hey, make sure everything's still in this regime or whatever it is, this regime, doesn't work. Right? A, it throws off the optimization, right? Changes the weights so they're not actually where the gradient says they should be pointing. But B, it makes a very non-expressive neural network. Okay, and so what batch normalization does is like a very simple trick. Instead of taking the weights and centering them to 0 and normalizing them by their standard deviation at each layer, you just have 2 new learnable parameters. One is how much you subtract from all the weights. That's this beta term. And one is what do you divide the output of each layer by? That's this gamma term, or multiply by. Right, so this normalization is shifting and rescaling. Those 2 parameters at each layer just become learned weights. TensorFlow does learn this way. Right? And so that simple idea really changed everything. Okay? So this mean, right, is now this learnable parameter, but you need to compute it as an average, right? Its influence is learned by applying it to many examples or along many pixels, right? It's like, where am I applying this beta to at each iteration? That's the question. And you have a number of options. So here's a data cube where the spatial dimensions are shown vertically, the height and width of the image, the number of channels in the layer is shown with C, and the number of examples is shown as N. So you have the freedom to apply normalization along different dimensions of this data cube. Batch normalization applies it across the images, right? Across a lot of examples for each channel. So in other words, each channel at each layer is going to get its own beta and gamma parameter. Layer normalization gives a unique beta and gamma parameter for each example. Instance normalization and group norm are more selective than that. It applies a different beta and gamma parameter for actually each instance, and then group is a selected group of the channels, not all the channels. And so those are all just simple options. You can choose whichever one you like. When in doubt, use batch norm. It just works, generally. But maybe it doesn't, and then you have to try something else. But generally, it works. Okay. Dropout is another reason why deep learning works really well. Okay, so dropout was in my code that I showed on Monday. It's a single line you can add kind of anywhere you want in your Keras flow. But generally, you want to add it after your convolutions and before your fully connected layers. Generally, it's good practice to add a dropout term before each fully connected layer. So if at the end of your neural network you have 3 fully connected layers, it would be a good idea to do dropout, fully connected layer, dropout, fully connected layer, dropout. Okay? And it's just one extra line you write in Keras. So what does dropout do? Dropout is simply freezes certain weights and doesn't allow them to update or be applied really in the evaluation, actually. So at each iteration, you just randomly subselect a set of weights, rather TensorFlow randomly subselects a set of weights to not use during evaluation. That's it. Why does that work? I'm not sure. I don't think anyone really knows. But it reflects the way our brain operates, right? Certain times there's lots of neural pathways through our brain, and certain ones are selected at certain instances to achieve the same task, right? So it gives redundancy to the computational flow. Second, it's memory efficient, right? It helps memory-wise. Third, it's like this random kicking of the person learning to ride the bike. It gives that random perturbation to your optimization pipeline to make sure the neural network is remaining robust, right? It's not relying on a single weight to really make the difference between getting that cat or dog classified. Because you're turning that off X% of the time, it's going to have to find some other weights to really help it achieve the goal, right? So I think all those reasons put together are probably the best way to kind of summarize why dropout works. So this term P is up to you, right? P is called P because it's probability, but really it's just what percentage of neurons do you want to turn off. When in doubt, 50% is a good choice. Yeah, you use this tf.layers.dropout function. It might be even simpler. That might be TensorFlow 1.0 code still. It's linked to in the example code. Okay, and so during training, you use dropout to make sure your neural network is robust. And then in testing, TensorFlow will do this automatically unless you tell it otherwise. All of the weights will be used for testing. Right, so the dropout process is just used during training to really make the network more and more robust. Okay. During testing, it's then taken away and you just pass it through and all the weights are applied. But you need to multiply all your weights by 1 minus this probability, right? So you rescale everything. We want to always split our data set into different categories and do that ahead of time. Here I'm adding a new category because it is useful to do this if you have enough data. We have training data. I'm adding this orange box. It's called validation data. So it's generally good practice when you make these neural networks to have validation data because you're going to keep changing your neural network to do different things, to optimize different things, make sure things are working, right? And then each time you want to do that, you want to test it. How well did that little change make this better? How well? So each time you do those hands-on changes, you're kind of cheating because you're looking at how well things worked with some quote-unquote unseen data. but then using those insights to then improve your network. So even though you're not trying to, by doing this process of being an engineer and repeatedly checking how well you're doing, you are tailoring your neural network to a particular data set. Then a real true evaluation of how well your network works is when you're done with all of that and you say, okay, now it's the final test, because the test data is like, hey, you're deploying your system into the real world. It's no longer in your hands to engineer, it's out there, and you want to make sure it really works, okay? So that's, if you have enough data, that's best practice. Oftentimes there's not enough data, and so I understand. I'd say like kind of good practice or general practice is to have in, let's say, 60 or 70% of your data should be training, 10% should be validation, and then 20% should be testing. And those kind of can all fluctuate. If you have really not enough data, there's ways to train your network multiple times. Each time you'll set aside a kind of random or different subset of your data for testing. And so for each evaluation, because you're retraining a network from scratch, it's never seen this data set you set aside. And so you can train the network and have this unseen data and then do that, let's say 10 times, and statistically average all of those tests and get a good assessment. That's a good point to stop. We are going to talk about auto differentiation and backpropagation all in one class. It'll be great.